A magnitude 4.2 earthquake has just struck. Two of the world's most dangerous fault lines meet here. This is the strongest quake in... Stay with me until the end. I'll explain why this small earthquake is a warning sign. It has been decades since California has seen this. What does it mean for the big one? Let's look at the data for the next major earthquake.
Before we get into the details, I want to make one thing clear. A magnitude 4.2 earthquake is not a disaster by itself. It may have shaken homes, rattled dishes, and woken people up, but it ended quickly. What makes this earthquake important is not how strong it was, but where it happened. Once you understand what lies beneath this location and how stress has been building there for many years, you'll see why this event is much more important than the magnitude alone suggests. Let's go through everything step by step, beginning with the earthquake itself. Here's what happened early on the morning of July 12, 2026. At about 3:30 a.m. local time, a magnitude 4.2 earthquake struck near Frazier Park, California, about 70 miles north of Los Angeles. The earthquake started about 13 kilometers below the ground. People felt the shaking across much of Southern California, including Santa Clarita, Palmdale, and parts of Los Angeles and Orange counties. The USGS Shake Alert System sent out an early warning just before the shaking reached nearby areas. Thankfully, no injuries or major damage have been reported. At first, different sources reported slightly different magnitudes because the data was still being analyzed. Early estimates ranged from about 4.1 to a revised 4.4 as more seismic stations provided information and scientists refined their calculations. These small changes are completely normal after an earthquake and do not change the importance of where this earthquake occurred. If you're not familiar with the area, Frazier Park is a small mountain community along Interstate 5 near the Kern County line. Many people drive through this area while traveling between Los Angeles and California's Central Valley without giving it much thought. It is a quiet place that rarely appears in the news. That is exactly why this earthquake caught the attention of scientists who know what lies beneath the ground there. By itself, a magnitude 4.2 earthquake is not unusual in California. The state experiences thousands of earthquakes every year, and most are so small that people never feel them. In a normal year, only about 15 to 20 earthquakes reach magnitude 4.0 or higher. In North America, only Alaska records more earthquakes each year than California. That shows just how active California is when it comes to earthquakes. So why is this earthquake so important? The answer is its location. It happened almost exactly where the Garlock Fault meets the San Andreas Fault. This meeting point is one of the most closely watched and potentially dangerous fault intersections in California. According to historical earthquake records, this exact location has not experienced an earthquake this strong in at least 26 years. When a fault junction this important stays quiet for decades and then suddenly produces a noticeable earthquake, seismologists pay close attention because it may show that stress is shifting within the larger fault system. To understand why this matters, we first need to understand how these two fault systems work. The San Andreas Fault and the Garlock Fault are both strike-slip faults. This means the two sides of the fault move sideways past each other instead of one side moving up or down. The San Andreas Fault is a right lateral strike-slip fault. If you stood on one side of the fault and looked across it, the opposite side would appear to move to your right. The Garlock Fault works in the opposite direction. It is a left lateral strike-slip fault. On a map, the Garlock Fault runs from east to west and meets the San Andreas Fault. At that meeting point, the San Andreas Fault bends because of the forces acting on it. It helps to imagine two huge blocks of rock slowly sliding past each other in opposite directions year after year. In some places, they become locked together instead of moving smoothly. As time passes, stress builds up in those locked areas. Eventually, the stress becomes stronger than the friction holding the rocks in place, and the energy is released suddenly as an earthquake. Where the Garlock Fault meets the San Andreas Fault, these two massive fault systems push and pull against each other from different directions. This creates a very complex pattern of stress that is difficult to predict. The bend in the fault is especially important. In earthquake science, bends and curves along major faults often allow stress to build up more unevenly than it does along straight sections. Because of this, geologists believe these areas are more likely to produce large earthquakes. The shape of the fault makes it harder for stress to be released through many small earthquakes, allowing more energy to build up over time until a much larger earthquake eventually occurs. The Garlock Fault has remained locked and under heavy stress for a very long time. Scientists have studied evidence of ancient earthquakes preserved in layers of soil and rock, a field known as paleoseismology. This evidence shows that the Garlock Fault has experienced major ruptures in the past, with the ground moving about 2 to 3 meters along the fault. Movements of that size are consistent with an earthquake of around magnitude 7.5. However, there is one very important fact. There is no historical record of the Garlock Fault producing an earthquake anywhere close to that size during the time for which we have written accounts or modern instrument records. Scientists currently estimate that the fault has probably gone between 500 and 1,000 years without a major rupture. That means stress has been building along the fault for hundreds of years, with very little opportunity to be released. To put that into perspective, if the last major earthquake happened between 500 and 1,000 years ago, it likely occurred during the medieval period in Europe. That was long before California had been mapped, settled, or even visited by European explorers. Faults do not simply lose the stress they build up over time. The rocks on both sides of the fault continue to move slowly, lock together, and store more and more strain energy until the friction holding them in place is finally overcome and a large earthquake occurs. Scientists have also been concerned about increasing stress on the Garlock Fault for several years. In 2019, a magnitude 6.4 foreshock struck near Ridgecrest, California. Just one day later, it was followed by a much stronger magnitude 7.1 earthquake, which was the largest earthquake to hit California in more than 20 years at that time. According to calculations by the USGS, the Ridgecrest earthquake sequence increased the stress on the Garlock Fault by about 30%. In other words, scientists already believed the Garlock Fault was overdue for a major earthquake before the recent Fraser Park event, and the Ridgecrest earthquakes increased that stress even further.
Pinpointing the exact scale is key. Across California, the stress builds up. We track every fracture in the rock to see how mountains rise over millennia.
Then, only a few weeks before the Fraser Park earthquake, scientists published a major study that modeled about 1,000 years of earthquake activity in Andreas and San Jacinto fault systems. The study found that stress levels are now at an all-time high.
This new magnitude 4.2 earthquake, which occurred right where the built-up stress on the Garlock Fault meets the southern San Andreas Fault, and it becomes easier to understand why seismologists are paying such close attention. It also helps to look at the history of major earthquakes in this region over the past 200 years. In 1857, the powerful Fort Tejon earthquake, estimated at magnitude 7.5, struck near this same area. Farther south, a magnitude 7.4 earthquake affected the San Diego region in 1800. Then, in 1952, another magnitude 7.5 earthquake struck the region, although that event occurred somewhat east of the main San Andreas Fault rather than directly on it. One of the most interesting patterns is where the largest earthquakes have happened in recent decades. Most of the major seismic activity has been concentrated farther east, in the Mojave Desert and the eastern California shear zone, instead of directly along the San Andreas Fault. The 2019 Ridgecrest earthquake sequence followed this same eastern pattern, as did a magnitude 7.1 earthquake in 1999 and another major earthquake in 1992. Meanwhile, the western side of the system, including the San Andreas Fault itself, has remained relatively quiet for many years. There is another important historical event to consider. In December 1812, two powerful earthquakes, estimated at about magnitude 7.5 and 7.1, struck the same general region of Southern California. Together with the 1857 Fort Tejon earthquake, these events provide a rough picture of how often this part of the San Andreas Fault has produced major earthquakes over the past 2 centuries. They also show how long it has been since the fault itself last experienced a major rupture. Long quiet periods like this are one of the main reasons seismologists remain concerned, because they often suggest that stress continues to build along a fault that has not released its energy for a very long time. There is another important pattern to understand. Earthquake activity can slowly change location over time. Researchers have found that, in this part of California, seismic activity can gradually shift from east to west and then back again over periods of 50 to 100 years or even longer. Since many of the recent major earthquakes, including the Ridgecrest sequence, have occurred on the eastern side of the fault system, some scientists believe the pattern may now be slowly moving back toward the west. If that is true, it could increase the future earthquake risk on the Garlock Fault and the southern San Andreas Fault, right where this new magnitude 4.2 earthquake occurred. This slow movement of earthquake activity is not an easy idea to understand because it happens over such a long period of time, often much longer than a person's lifetime. A good way to picture it is like a very slow-moving pendulum. For many decades, earthquake activity may be concentrated in one group of faults, and then, over time, it gradually shifts toward another group. If this pattern is happening here, then the recent series of earthquakes in the east, including the Ridgecrest sequence, may represent the end of one cycle, while stress begins shifting back toward the western junction where the Garlock Fault meets the San Andreas Fault. These events are also not happening by themselves. Earlier in the summer of 2026, a magnitude 5.6 earthquake struck near Redwood Valley in Mendocino County. It caused local damage and left thousands of people in Northern California without electricity. Then, only a few weeks before the Fraser Park earthquake, scientists published a major study that modeled about 1,000 years of earthquake activity along the southern. When talking about this point, I want to be very careful when talking about this point because it is easy for people online to make too much of this kind of connection. Solar flares happen regularly, often several times a month during the most active parts of the solar cycle. Earthquakes also happen every day around the world. Because of that, it is normal for the timing of some solar flares and earthquakes to overlap simply by chance, without any real connection between them. The mainstream scientific view is still that there is no proven or reliable evidence showing that solar activity directly triggers earthquakes. I mention this only because it adds an interesting piece of context to an already unusual day, not because it should be considered strong evidence by itself. So, what does all of this mean going forward? Based on the evidence available today, several major fault systems across California appear to be under unusually high levels of built-up stress at the same time. The Garlock Fault is still considered to be long overdue for a major earthquake, possibly as large as magnitude 7.5 or even greater. The southern San Andreas Fault has also gone a very long time without a major rupture along its main fault line, and recent studies suggest that the amount of stress stored there is now equal to, or possibly greater than, anything seen during the past 1,000 years. Northern California is also showing signs of increased earthquake activity. One example is the magnitude 5.6 earthquake that struck near Redwood Valley in June. At the same time, the San Francisco Bay Area remains an area of concern because it contains several major fault systems, including the Hayward Fault, the Green Valley Fault, and the Calaveras Fault. Many scientists believe these faults are also overdue for a significant earthquake. The risk is made even more challenging by the fact that some faults remain unknown until they actually produce an earthquake. A good example is the West Napa Fault, which was not officially recognized until it generated a magnitude 6 earthquake in 2014. The West Napa Fault is an important reminder of how much there is still to learn about earthquakes. Even after decades of detailed mapping, satellite observations, and advanced monitoring equipment, scientists can still be surprised by previously unknown faults that only become visible when they suddenly rupture. This is one of the strongest reasons why earthquake preparedness is important across all of California, not just in the areas currently receiving the most attention from scientists and the news. There is a possibility, though not the most likely one, that a future major earthquake could rupture both the Garlock Fault and the southern San Andreas Fault at the same time or in quick succession. Such a multi-fault rupture would likely produce a much larger and more complex earthquake than either fault alone. Recent earthquakes around the world have shown that ruptures can jump between faults, which is why researchers consider the Cajon Pass earthquake gate so important. It may determine whether a rupture stays on one fault or spreads across multiple connected faults. This is not meant to cause panic. Earthquakes of this size are common in California and usually cause little damage. However, this magnitude 4.2 earthquake occurred near one of the state's most closely watched and long overdue fault junctions. Combined with the stress that has been building across Southern California's fault system, it is an event scientists believe deserves careful attention. The key message is that California's major faults have been accumulating stress for a long time, and this earthquake may be another small but important piece of that.
Beneath California, immense forces are at play. Scientists race to monitor the growing tension. On the surface, a deceptive calm masks the danger. A future major earthquake could rupture both faults at once. The Cajon Pass is the earthquake gate. It may determine our future.
Identified an area called Cajon. The study also identified an area called Cajon Pass as a possible earthquake gate. This is an important junction that could determine whether a future earthquake stays on one fault or spreads to nearby fault systems, creating a much larger event. This idea is important because it changes how scientists think about the worst-case earthquake scenarios in Southern California. In the past, researchers usually treated the San Andreas Fault and the San Jacinto Fault as mostly separate systems, with each capable of producing its own large earthquake. However, this new study suggests that, under the right conditions, an earthquake that begins on one fault could pass through Cajon Pass and continue onto the other fault. If that happened, the two fault systems could rupture together, creating a much larger earthquake than either one could produce by itself. This possibility greatly increases the potential size of the largest earthquake that could occur in this region. One of the researchers involved in the study, who is a professor and director of the California Earthquake Center at the University of Southern California, pointed out that Southern California has not experienced a major earthquake directly affecting a large urban area since the Northridge earthquake in 1994. Based on the amount of stress identified in the new study, he believes that releasing this built-up energy would probably require an earthquake of magnitude 7 or greater. Scientists estimate that an earthquake of that size today could affect nearly 24 million people living in the greater Los Angeles area and the Inland Empire. That gives an idea of just how serious such an event could be. It is also helpful to compare this with the Northridge earthquake. Although the 1994 earthquake was smaller than the scenarios described in the new study, it still caused billions of dollars in damage and remains one of the most expensive natural disasters in United States history. A magnitude 7 or larger earthquake on the southern San Andreas Fault today would strike a region with millions more people and much more infrastructure than existed in 1994, making it a much larger and more damaging event. When you put all of these facts together, the long overdue Garlock Fault, the extra stress added by the 2019 Ridgecrest earthquakes, the new research showing record high stress levels along the southern San Andreas system, and now a magnitude 4.2 earthquake at this historically quiet fault junction, it becomes easier to understand why seismologists believe this small earthquake deserves close attention despite its modest size. At the same time, it is important to be clear about what this earthquake does and does not mean. A magnitude 4.2 earthquake is not proof that a much larger earthquake will happen in the next few days or months. Modern science still cannot predict earthquakes with that level of accuracy. Instead, this earthquake should be viewed as another important piece of information that adds to a growing body of evidence showing that stress has been building across this fault system for a long time and that the region remains overdue for a major earthquake at some point in the future. A useful way to think about earthquakes like this is to imagine each one as a single pixel in a much larger picture. By itself, one magnitude 4.2 earthquake does not tell scientists very much. But when it is combined with decades of paleoseismic evidence, recent stress modeling studies, what researchers learned from the Ridgecrest earthquake sequence, and the fact that this earthquake occurred at a historically quiet and very important fault junction, it becomes much more meaningful. This is how modern earthquake science works. Rather than relying on dramatic predictions, scientists carefully build a clearer understanding over time by collecting and studying evidence gathered over months, years, and even decades.
California's major faults have been accumulating stress. This earthquake may be another piece of that picture. Whether on the Garlock Fault, the Southern San Andreas Fault, or the Bay Area, preparedness is essential. Review your emergency plan today. Keep enough food, water, and medical supplies. Have backup power and know where to take cover. Make a family communication plan. I will continue USGS data, aftershocks, and updates from researchers. If significant new information becomes available, I will provide another update. Stay safe, and I'll see you in the next report.